right, well, welcome back, everyone. Thank you for staying with us this afternoon. My name is Leon Bruner. I'm adjunct professor in the Institute for Integrative Toxicology here at Michigan State, and have been very active with Chris for quite a number of years, and I'm really grateful to see everyone here this afternoon. So just to let you know how the rest of the day is going to go, we're going to have two more speakers, and then what we're going to do is do a quick reset because we're going to have a panel discussion after this presentation. So we're going to slide this podium back and set up some chairs. So there'll be a short break while we do that, and then we'll roll into the panel discussion, just so you know what's going to happen. So our next speaker this afternoon is Dr. Craig Curtzwiler, who is Dr. Curtzwiler is an assistant professor in the Polymer and Food Production Consortium at Iowa State University. His research is centered on developing safe and sustainable materials for adhesives, coatings, and polymers in the packaging and automotive industries, including bio-based, compostable, and recycled polymers. His group is currently focused on understanding chemicals of concern in recycled plastics and mitigation strategies. Greg has published more than 40 publications and has 9 patents to his credit in the areas of food packaging, sustainable polymers, and nanotechnology. So Greg, welcome to the stage.
Thank you for the introduction, and certainly welcome everybody back from the break. I know it's going to be a little bit longer of a day, and so we appreciate the previous speakers so much, right? Because they really set up really how the rest of this talk is going to go, at least for me, and then of course Dr. Fisher at the end of this. But really what we're focusing on is what kind of chemicals could be found in some of these recycled plastics. So we've talked about legacy materials. There are a lot of additives that are no longer being used or in the process of being banned, or there are thresholds and so forth. And so really what my research group is, again, it's within the Polymer and Food Protection Consortium Center at Iowa State University, is focusing on is trying to understand the concentration of these chemicals, perhaps some of the exposure risks, and so forth. Okay. So as an outline to this talk, we're going to start with kind of an introduction to restricted substance lists, what they mean, kind of how they're used in the food packaging industry, and then we'll dive into some experimental work of the variety of different chemicals that we've detected in polyethylene and polypropylene. Also looking firstly at the non-intentional added substances. So again, this is like more of like a screen, followed by some of the targeted endocrine disrupting chemicals like phthalates and bisphenols. So huge disclaimer, I know a lot of you or some of you are toxicologists. I am not. I am a polymer engineer, and I use Kramer classifications as the best way for me to be able to understand potential exposure risks. Other than that, my goal is to be able to understand how much material could be eventually or potentially exposed to during the use of these materials. So for restricted substance lists, this is a list of chemicals that are restricted to or banned to a specific threshold. So phthalates, bisphenols, PFAS, these are very commonly added to restricted substance lists. What we've done is surveyed a lot of the public restricted substance lists that are out there from food packaging companies mainly. But what becomes really important is that there is no universal or standardized restricted substance list in the industry. This can make it really challenging when we're trying to use recycled materials or even new materials to be widespreadly used throughout the industry. So we survey these materials, determine their associated threshold concentrations to be able to understand a little bit more about the potential consumer and environmental safety of what the current industry is doing. Before we dive into that, this is a publication that was recently published. Okay, this was September 17th. This was done by the Food Packaging Forum. Since then, there have been 20,000 accesses of this publication, and this was related to the exposure that humans have to chemicals that are in food contact materials. So their findings claim that there are over 1,800 food contact chemicals that are known to migrate from food contact articles that are used to store, process, package, and serve food. And many of these have hazards, properties of concern that have not necessarily been tested for toxicity. So this is a huge area that we need to fill a lot of data gaps, right? So basically in this, they use data mining techniques to be able to look at the amount or the types of chemicals that were in a variety of like human blood, in the hair, and so forth in the body by a number of different databases. So there's a significant amount of potential exposure from a variety of these different chemicals, and we'll dive into a little bit about what, again, the restricted substances are, some of the different additives that are being used in polymer manufacturing, some of the legacy materials that could potentially create some hazards within the human body. So again, what we did is we went to the literature and looked at these restricted substance lists from the variety of different manufacturers, but we also looked at regulatory, so like Proc 65, for example, Toxic Packaging Clearinghouse, and then again, the different restricted substance lists. We sorted these into what would potentially be intentionally added substances that are going to be in packaging. So again, they'd be additives, whether they're performance additives, processing aids, stabilizers, slip agents, or whatnot, as well as non-intentionally added substances. So these could be degradation byproducts, degradation products of the polymer, of the additives, or potential consumer abuse, or just contamination in the recycling stream if we're going to be looking at food substances versus non-food. Of course, as you are going to utilizing materials for food contact, they need to go through the food contact notification system. So these are basically, we have some idea about what could be in the package based off of and the potential exposure, because this testing is required as new additives are being introduced into the food packaging industry. So basically what we've found is the different reasons why we would have some of these chemicals that would be on a restricted substance list. I mean, the easy one is legislation, right? I mean, so if there are going to be phthalates or bisphenols that are going to be regulated for a certain application, then clearly this is going to be something that has to be on a restricted substance list, but also the scientific community. So as more toxicology, more understanding is being developed based off of some of these different chemicals, as well as the potential exposure, right? So these are going to be ways that we're going to get a little bit more of that understanding and why some of these chemicals would eventually find their way on to a restricted substance list. Then, of course, eco-labels. So part of this also can become from, you know, I'm going to say PFAS probably too many times during this presentation, and phthalates, but these have become really hot topics, right? The toxicity is starting to become more well understood. They've been used in a lot of areas all over in many different industries, and they're also in the environment basically everywhere. Basically, if you're breathing in this room right now, you have PFAS in your bloodstream, right? They found it in the Marianas Trench. They found it in polar bears in the North Pole. So it's basically an environmental contamination that we really don't have a lot of control over, but yet we're still potentially being regulated to something that could eventually potentially remove all packaging from the industry. So trying to get a grasp on understanding why some of these chemicals could be present on a restricted substance list or in regulatory becomes important for us as we're building our libraries of understanding for utilizing some of these potential waste products, right? Because that's what recycling is dealing with, is waste, back into food packaging. So when we look at things that could come out of packaging or plastics in general, so these are going to, you know, what we're concerned with more so is the migration effect, right? Because basically if an additive is in a polymer, you're going to need to have it be removed from the polymer into food or whatever, whether it's on your hand, and then eventually make its way into your body or the environment in some manner. So that's going to be a migration type mechanism. And again, these can be kind of divided into two different classifications. One is an intentionally added substance. These are known, these are expected, right? So again, these could be the polymer additives, these could be inks, these could be like photoinitiators from the ink in the manufacturing process. But again, non-intentionally added substances where basically they have no technological effect or no positive technological effect of the material. So these can be a result of the degradation process of the material or additives. They can be impurities during the manufacturing process, a variety of different chemical reactions. As Ann mentioned earlier, as you recycle and grind and they go through all of these different processes, we start to change the molecular structure. So the rest of the chemicals that are in the packaging, also of the plastic itself, all have different chemical structures depending on its life, whether it's hanging out in the ocean doesn't want to hang out in the ocean. But if it's in the ocean for 15, 20 years and it has a significant amount of UV exposure, it will be different from a plastic that's been buried under a landfill for the last 30 years. But also how those products were put together will influence what additives will be present, right? Because if it was done 30 years ago, there are different regulations as there are today. And so that will influence what could potentially be present. One of the things that becomes a huge question mark, though, is we don't know how diffusion changes in recycled polymers. The molecular structure has changed. We measure oxidation in polyethylene, polypropylene, polyethylene terephthalate. We do this all the time. We've been studying this for decades. But what we don't yet still understand is how are those additives, then that diffusion changes as a result of that. Initially, going through that food contact notification to get approval for use of some of these chemicals and these additives, that was no. But as we, again, so this becomes a huge question mark that our group is currently working on, trying to develop a deeper understanding of. So some of the pretty traditional chemical groups that are compiled in the restricted substance list. So I don't want to read these to you folks because it's kind of a long laundry list. On that right-hand side there are going to be some of the more specifics, but things like monomers, additives, adhesives, some of the dyes and colorants, heavy metals, PFAS, flame retardants, and so these are very common themes that we see in the restricted substance list. So we found roughly 939 different chemicals from our review of the literature of these restricted substance lists. So again, clearly this is not something that it's going to be very challenging to be able to be compliant with all of these. But we also then wanted to understand what are the relative toxicity, again, not a toxicologist. So we used the Kramer classifications for this, class 1 being the lowest risk, class 3 being the highest risk. The vast majority of the chemicals that are going to be on that restrictive substance list, again, globally as we compiled them, are going to be in that Kramer class 3. So some of them were undefined, and the Kramer classification is based off of the molecular structure and basically the inferred toxicology of that. But again, the most of these were probably not surprisingly to be the more toxic versions of these chemicals. So as we take this information and try to understand some of those different thresholds, we wanted to understand a lot more about what's going to could potentially be used, either go back into food packaging or perhaps other products. Again, most of the folks that we work with are more interested in food packaging. We do have some that are in furniture as well. They have these same kind of restrictions, okay? So this becomes relevant to really most industries that we've come across. So how we've collected a lot of these samples, we actually physically show up at MRFs. We drive there. The image that you see up there, that is a mixed 3 through 7 bale. So that's basically a lot of the plastic that's not being used and that has lower value. And these particular ones were destined for a landfill, and these things are absolutely nasty. We drive them back to our facility. We hand sort them. We found diapers. We found chickens. We found all kinds of random things in these bales. And so we've collected bales from New Jersey, Chicago, Texas. We're in Iowa, so clearly we have a couple of those. Wisconsin, California, and really try to understand what's the composition of plastic in the 3 through 7 bales. And it varies by MRF. It varies with the sorting technology. So that becomes a really critical piece as well to understand when we're trying to increase recycling rates by having good valuable materials, and for the advanced recycling, having that knowledge of what's in these bales that are potentially going to a landfill becomes really critical. So we've also collected materials from commercial recycling facilities from around the world, and that could be PET, polypropylene, and polyethylene. But from these material recovery facility bales, we also wanted to have a deeper understanding of the types of additives or contamination that could be in food grade materials and non-food grade materials. So we use polypropylene as kind of our case study for that, and we sorted then based off of what we could see the product was. So again, if it was like cat litter, it would go into non-food. If it was sour cream, it would go into food. So we further sorted those to finish out the rest of the study. So we took the material, sorted it by the code as you saw there, then we granulated it. We went through a very small trauma wash, and so our goal, again, partnering with also recycling facilities around the country, Our goal is to be able to try to mimic this the best that we can. We also follow the Association of Plastics Recyclers guidelines for a lot of the different washing techniques that are utilized. And so for this initial piece, this is kind of the route that we took. We shredded it, washed it with the trommel wash. Basically, this removes a lot of the gross contamination, so rocks and dirt and things along those lines. Then we went through a simulated friction wash, which consists of just water, sodium hydroxide as a caustic, and then Triton X100 as a surfactant. From there, we did 2 different routes. One of them was a full dissolution. So again, there are 2 different kind of thoughts that we were trying to get to here. One was, I want to know the world. I want to know everything. If I ate this plastic and that plastic dissolved in my body, what am I actually ingesting? Then other than that, we also did a solvent soak where we used xylenes, which is going to be an aggressive kind of solvent for this, to try to, again, worst case scenario, if I have something that's going to be in a package at maybe 80 C for weeks on end, we want to know what's going to be that kind of worst case scenario. So we're also in the process now of using food simulants that are going to be typical for the food contact notification system. But we then, after we collect our samples, we filter it to get rid of all the rest of the solid materials. Then we characterize it with a couple of different methods. So again, for our survey mode, which we're trying to just see yes or no, is this present? What could potentially be in there? We're using a GC mass spec. Now there's also, then we get the mass spectrum and then use the latest mass spectral library from NIST to be able to identify what these are based off of their signatures. There's a caveat to this. Now that we have the mass spectrums, that's great, it's a very sensitive tool, but since we're looking for everything, that increases our limits of detection, okay? That decreases our sensitivity. So we're not seeing necessarily everything that's in there if they're in very low concentrations. So for some of the chemicals that we're a little bit more interested in, so again, phthalates, bisphenols, PFAS, we're gonna use a tandem mass spectrometer. Basically, that allows us to be very, very selective in what we're trying to quantify. And so we can get very good detection limits from those techniques. We use GC triple quad as well as an LC triple quad for that. So for the survey of a variety of different chemical or of recycled materials, again, we used 23 post-consumer polyethylene and polypropylene samples. Some of them were from material recovery facilities. Some of them were for recyclers, but we also wanted to compare what would it be like, or what the chemicals that we would observe in a virgin polyethylene sample, and we screened these again for the NIAS and IS. So this was what we did with the xylenes for 2 weeks at 40 degrees Celsius. We basically summed up all the different chemicals that we detected from those different samples. For virgin polymers, we used low density polyethylene, linear low density polyethylene, medium density polyethylene, high density polyethylene, and there was a polypropylene one in there between the 6. And there were basically 9 different compounds. So some of these, again, we got to keep in mind that in virgin compounds, they may not necessarily have a variety of different additive packages yet for their application, okay? So some of the, virgin polymers, not virgin polymers. So this is not new plastics, not new plastic. Okay, it depends on where in that manufacturing process you get that. We can still have additional additives that are being put into these materials further downstream in order to manufacture what we need to manufacture. But from the 23 different post-consumer samples, we detected 52 different compounds. Okay, so when we look at the detected compounds in each of these classes, as we see here below as a percentage, keep in mind that for virgin we saw 9, and for the recycle we saw 52. So with the virgin materials, we saw alcohols, ketones, hydrocarbons. Again, you'll see that there was a higher percentage of hydrocarbons in the recycled materials. Again, since we're working with polyethylene, polypropylene, this is not necessarily surprising. Some of the degradation products, you'd expect them to be hydrocarbons, right? They're made from hydrocarbons. As they break down, they're going to be still hydrocarbons. Organic acids and phenols and amines. And so again, we're seeing a lot of the different additives. We've seen phthalates, we saw bisphenols, and we saw surfactants. The surfactants piece in the recycled materials is something that we're going to get back to later in the talk. This would be a very interesting observation as we move forward in the mechanical recycling world. So we also wanted to see if we can wash these materials to start to remove some of the different contamination, right? So as Dr. Van Lanes was showing, his approach is great in the fact that it could potentially remove some of these other additives from the core of the polymer, right? And so what we're focused on in my group is more so, again, on the mechanical recycling world. And so when we go through the process of washing and cleaning, this is going to be mainly surface limited. Water doesn't penetrate into polyethylene. Water doesn't penetrate into polypropylene. But we did see a rather significant decrease in the number of compounds detected. So again, number of compounds detected. We're not quantifying things. We don't have concentrations. Concentrations become very, very critical. So this is something that we're moving forward with and trying to be able to develop that understanding. But just simply rinsing with water did not remove a significant amount of the chemicals that were detected on the surface. Starting adding some of the surfactants and the caustic allowed us to observe a reduction in the number of compounds that were present. So again, we further sorted these between the food materials, or food grade materials, and non-food grade materials for the compounds that were detected by the Kramer classification, and they were pretty similar. Right, we don't necessarily know the composition. I mean, I have them; they're in the papers and that for us. If you wish to review those, we'd gladly send you the references for those. But it's a laundry list of chemicals, right? And so the toxicity, though, is more so what we were looking at, trying to understand with using the Kramer classifications, and what was detected between food and non-food. Both of them were class 3, around 50%. That's practically the same, right? And if we were to mix the not food and the non-food together and compare that to the virgin materials, we were, again, pretty similar. So the class 3 were 37% for the virgin materials and about 40% for the mixed PCR. So again, we don't necessarily know what these chemicals are here, but just looking at this as a class, it was very interesting to see that the potential toxicity of the different additives that were going to be within these materials were pretty similar for the distribution. So to kind of summarize that section, so a majority of the detected substances were class 3. So again, that would be if we assume that there's 100% migration of these chemicals, that could potentially cause some risks, right? But is this a good assumption? The answer to that's no, right? Some of these higher molecular weight molecules, the diffusion coefficients are much lower, right? So they're designed to hopefully stay in the polymer. So again, that's where hopefully some of the stuff that we're going to be doing going forward with using food simulants to be able to develop a little bit more of an understanding of the true risk under different conditions of use. So that's another consideration, is the condition of use, whether it's going to be room temperature storage, refrigerated, heated in an oven as like a dual ovenable type of application. Those are all very critical things to try to understand for potential risk. So those are what we're doing going forward for quantification of those studies. So if we dove into a little bit deeper into some of the chemicals that we're specifically interested in, the phthalates and bisphenols, and so there's the kind of laundry list of phthalates that we're looking at, and the bisphenols as well. And so these generally came from, so ASTM standard has some for children's toys. The Toxic Packaging Clearinghouse has their list as well. That was also generated from some of our industry partners that they were specifically interested in. So again, we use that GC triple quad to be able to do the quantification and get those much lower detection limits. And we did detect them in just about everything, right? And this is not necessarily overly surprising in the recycled material, but we did also detect them in the virgin materials as well, right? So again, some of them may not have their full additive packages, but some of these are also used as part of the actual polymerization process as part of the catalyst package. And so what we did observe, which was kind of interesting, and this one here on the top left-hand side there, diethyl phthalate. So this is going to be one of the more water-soluble phthalates of the ones that we detected. As we go through some of the washing, we did start to see a slight decrease in that phthalate present. So again, from a mass balance point of view, if we're removing some of these contaminants, where's it going? So if we're using water to wash a lot of these things, these contaminants or these chemicals of concern, however you want to kind of look at it, are likely going into the wash water. So we'll see in a second, that's where we wanted to follow that mass balance. So these were the 23 different polyethylene and polypropylene samples. This is going to be specifically from the MRFs, the polypropylene that we looked at earlier. Again, the recycled materials had more. But what was interesting, though, is that I don't recall any of the recycled materials that we ever tested that exceeded the incidental threshold by the TCPH at 100 parts per million. Most of these are going to be in that very low parts per million range. And so this was good to see that we could potentially have a lot more materials that we could use for food packaging, but we now know it's there, right? So what is the risk of exposure, and what does that look like from a consumer standpoint? Things could be compliant all day long, but at some point we still have to react to what the consumers are driving for and try to educate. And there was a question about education earlier about recycling. And this is a huge gap that as an industry, we really kind of need to focus on to be able to try to educate folks to make sure that what the information that they are getting is going to be actually relevant with respect to risk of using a variety of different materials. Okay, so as I mentioned, we're going to be pushing forward into understanding a little bit more about where some of these chemicals are going as we start to clean the surfaces. So we, again, took the same approach. We collected materials from the bale, we ground them, sorted them, then ground them, went through the trauma wash. But we're also looking at 3 different kinds of washes here that could be representative of what's happening in the industry. And so, again, some could potentially use what we call the friction wash, which is sodium hydroxide and a surfactant. Some of them may just be using a surfactant by itself. Some may be using a caustic by itself. But we're also in the process of developing an ultrasonic wash, which is basically just water that's going to be present to try to reduce the need for some of these other surfactants and so forth. So we took these materials, washed them 15 times. We did not clean the water in between. So as you can see, the dirt's getting darker as we move forward there. We'll just kind of dive into this. I think I'm probably going a little bit too long here, but basically what we ended up observing that if we have surfactant present, we actually are starting to remove and observe more phthalates that are going to be in that wash water. So as we move forward though and washed it multiple times, it was interesting to see that the concentration of the phthalates actually decreased the more it was washed. So that didn't really make a lot of sense. We were expecting to see an increase. But what we did was an observation that there were less bubbles in the wash itself, which suggested that the surfactant was also leaving with the plastic. So this was suggesting to us that we're actually could be contaminating good material, right? We're removing contaminants from one side, and if we can't remove it from the water that we're using to wash new material coming in, the surfactant and the phthalates are leaving with the other plastic that was just being washed. So that's another area of trying to do mitigation of those chemicals in the wash water that we're looking at as well. So just kind of to wrap all of this up, basically most of the things that were on RSLs are going to be class 3, Kramer class 3s, which would have the highest relative toxicity. Again, using a surfactant seemed to be important at reducing some of the surface contamination of phthalates. And that also then appeared to then change in concentration or leave with the plastic that we could potentially contaminate even more. So this is certainly something that we're very interested in monitoring and doing a lot more research on. So that's what I have. I'd like to thank IFINS, the Institute for Advancement of Food and Nutrition Sciences, for partially funding this work, along with the Polymer and Food Protection Consortium at Iowa State.
I think we have time for a question. We have one up front. Let me whiz up here and give you the microphone.
Thank you for presenting a great study. And I want to clarify some of the points. The first one is, when you utilize these 8 virgin polypropylene, are you using the pellet or the bottle?
So those would be from the pellet. So at that point, the first study that we were talking about, those were basically all from the pellet. So the MRF, we ground it all up and use that. And then for the recycled materials from around the world, those were all in pellet form.
Okay. The second one is when you're utilizing the thermal wash, I'm not clear about the terminology. So when you using the first cycle of the thermal wash, what is the cleaning process after the first running before processing the second run?
So the trauma wash, all it does is a drum. Like you think of like a washing machine, it just spins and then it just basically rinses the plastic off. And so again, that's to remove a lot of the dirt and rocks and things like that that could then fall through those holes in those screens, and then the plastic then moves forward before going into those other processes.
So you're not washing after the first running cycle.
After the trombone wash, yes, we do. There's the friction wash or those other kinds of washes that we're looking at, but we mainly follow the Association of Plastics Recyclers guidelines for the friction wash.
I'm still not clear about the result because you are investigating and characterize all different types of the chemical compounds existing in the surface of the polymer, and you don't wash after the certain amount of the cleaning. The residue can be remain in the top thermal wash equipment, and they can recontaminate the other.
It certainly could.
Yes.
Yeah, it certainly could.
So
We track the contamination or whatever the chemicals are concerned or whatever we can extract from the residual flake material that's been ground, and we track that through the different wash processes.
All right, thank you very much.
Thank you.